Hello everyone, welcome to my number theory lecture. In this lecture, we study divisibility. We begin with the following definitions. We say A divides B and write using this notation if there exists an integer D such that B equals A times D. In this case, we say A is a divisor of B and that B is a multiple of A. If A divides B is false, then we write this notation here, okay? And we say D is the greatest common divisor, GCD in short, of A and B, if D is the largest of all integers dividing both A and B. So simply speaking, if D is the largest common divisor, okay, if D is the largest common divisor, we call it greatest common divisor, okay. And in that case, we use this parenthesis notation, right, to denote, the greatest common divisor of A and B. Okay, we say M is the least common multiple, LCM in short, of A and B if M is the smallest of all the positive integers that are multiples of both A and B. In this case, we use bracket notation. So the least common multiple of A and B is denoted by the bracket of A and B. So here's an example. Let's say A equals 4 and B equals 6. So in this case, the divisors of A are 1, negative 1, 2, negative 2, and 4, negative 4. The divisors of 6 are 1, negative 1, 2, negative 2, 3, negative 3, 6, negative 6. So in this case, the common divisors of 4 and 6 are 1, negative 1, 2, negative 2. And in this case, the largest of all common divisors, okay? So, the divisors of both 4 and 6, that's 2, right? So 2 is the greatest common divisor of 4 and 6. And the positive multiples of 4 is 4, 8, 12, 16, 20, 24, 28, and so on and so forth. And the positive multiples of 6 are 6, 12, 18, 24, 30, and so on and so forth. Okay? So, in this case, common positive multiples of 4 and 6 are 12, 24, and so on and so forth. But in this case, the least one, the smallest one is 12. So, the least common multiple of 4 and 6 is 12. Okay, so the divisibility, right, has some important properties. Okay, so they are listed in the following theorem. So given integers a, b, and c, right, first the properties, if a divides b, then a divides b times c. If a divides b and b divides c, then a divides c. If the last property is if a divides b and a divides c, then a divides b times x plus c times y for any integers x and y. So in this case, the right-hand side, I mean, not the right-hand side, sorry, the bx plus cy, right? Okay. I mean, the expression in the right-hand side of the division notation, right? That's called a linear combination. Okay, that's called a linear combination of B and C. Okay, but the name is not that important, but yeah, that's what it is called. Okay, so let's prove this theorem, right? All these properties can be easily proven using only the definition of divisibility. So to work on the proof, let me move to my notepad. So here's the theorem. So first property is if A divides B, A divides B, and then if A divides B, then A divides BC. Okay, A divides BC. So let's prove this one first, and then we're going to move to next property. Okay, so for the proof, I'm going to use a different color. Maybe I choose blue. Okay, so proof. Okay, so we start with the assumption that A divides B, right? So A divides B. That's the assumption. So that implies that, okay, what that means is, the B, by definition, okay, by definition, B is a multiple of integer multiple of, the A. So B can be written as A times D for some integer, for some integer D. Okay, here, this big C is what? That's notation for the set of all integers, right? So that's what the notation we commonly use. Okay, so now this implies, so if we multiply each side of B equals AD by C, so then BC equals AD times C, okay? And integer multiplication is associative, as we know. So this is same as A times DC, and D times C, multiplication of two integers, is again an integer. So what do we see? A, in this case, B times C is an integer multiple of A. So again, by definition, in this case, A divides BC, right? Because BC is an integer multiple of A. Okay, so this completes the proof. Okay, so now we are moving to the second property. So second property, what did it say? What does it say? If A divides B, and B divides C, then A divides C. A divides C. Okay, that's the property. Okay, so we prove this one. Now, okay, so start out with the assumption that A divides B and B divides C. Okay, so A divides B and B divides C. That implies, again by definition, A divides B means that B is an integer multiple of A. So B can be written as A times D1. Likewise, B divides C means that C is an integer multiple of B. So C can be written as B times D2. For some integers D1 and D2. Okay, so now what we are going to do is the following. Okay, so we want to show that A divides C, right? That's what we are going to do. Okay, so here C equals B times D2, right? And B is A times D1. So I'm going to replace B by this right-hand side, the A times D1. So C equals A times D1 times D2. Now again, integer multiplication is associative, so this can be written as A times D1 times D2, okay, inside the parentheses. And the multiplication of two integers is again an integer. So D1 times D2 is an integer. So what do we see? We see that, right? So this expression tells us that C is an integer multiple of A. So by definition, the definition again, A divides C, right? So by definition, this implies that A divides C, okay? By definition, right? Okay, so now last property, property number 3. If A divides B and A divides C, okay? A divides B and A divides C, then A divides bx plus cy for any integers x, y. Okay, like I said before, this expression here, right? Bx plus cy, that's a linear combination. Okay, that's called a linear combination of x and y. Okay, so let's prove this. So we start with the assumption. So in this case, the assumption is A divides B and A divides C. Okay, so A divides B and A divides C. So this implies that, again, by definition, A divides B means that B is an integer multiple of A. So B can be written as A times D1, and A divides C means that C is an integer multiple of A. So C can be written as A times D2 for some, okay, for some integers, D1 and D2. Okay, now we are trying to show that in that case, under that assumption, A divides any linear combination of B and C. I'm sorry. Yeah, like earlier, I misspoke, right? Not the linear combination of X and Y, linear combination uh, of B and B, linear combination of B and C. Okay, uh, sorry about that. Right, so bx plus cy for any xy, integer xy, that's a linear combination of B and C. Okay. Okay, so going back to our proof, right? So, so what we are trying to prove is, under this assumption, A divides any linear combination of B and C. So this implies, okay. So to show you that, right? Uh, so we consider the following: any, okay, linear combination of B and C. bx plus cy. Okay, so that equals uh, we gotta work with that for any xy we gotta show that for any xy integer, two integers xy, the A divides linear combination bx plus cy, right? So to emphasize that, for any x, y. Okay, so I'm going to specify that x, y are chosen randomly. Okay, randomly, so just any x, y, two integers x, y. Okay, for any x, y, right? The linear combination, so b x plus c y, that equals, instead of b, I'm going to replace it by a dy. So AD1, AD sub 1 times x, right? And I'm going to replace C by AD2, AD sub 2 y. Now again, integer multiplication, okay, integer multiplication is associative. So, this can be written as A times d1 x, right, plus here a times likewise d2 y inside the parentheses. Now a is in common, so we can factor it out, right? We can factor a out. In fact, the property that allows the property of integers that allows us to factor a out is what? Distributive law, right? Okay, so integers satisfy distributive laws, right-left distributive laws, right? So a is factored out, and what's remained is d1 x plus d2 y. But then this d1x plus d2y, regardless of what x and y are, okay, regardless of what x and y are, this whole thing is an integer, right? So what you are looking at is a linear combination, of d1 and d2, but that's this whole thing as an integer. So they belong to C again. So what do you see? Bx plus cy, any linear combination of b and c is an integer multiple of a. So by definition, this implies that a divides bx plus cy. So this proves the property number 3. Okay, so we are done. All right. This is something we are going to learn, okay, in our in my next lecture, right? But let me give you a little heads up, okay, little heads up. So this is something called Bézieu's lemma. Okay, Bézieu's lemma. This is named after a French mathematician, Bézieux, right? So what does it say? It's the following. So there exists, right? There exists integers x and y such that the greatest common divisor of a, b is written as a x plus by. Okay, so in other words, the there's you can view this as this expression as an equation of two variables x and y. Okay, so you can always, so what the Bézieu's lemma says is you can always find a solution xy of this equation here, right? So this type of equation has a long history. Okay, so it goes back to the ancient Greek time, right? So people actually studied this type of equation, and they studied also like the how to solve this type of equations. So this type of equation is called a Diophantine equation. Okay, this is a oh, I meant to use green color. A Diophantine equation. This is named after a Greek mathematician, Diophantus. And so we're going to talk more about, the Diophantine equations, and also, like I said in my next lecture, I'm going to talk about this Bezout's lemma again. The reason I'm actually bringing up this Bezout's lemma uh, is to show you one thing. Okay, so assuming that we know this Bezout's lemma, well, actually we do know now because I just talked about it. Okay, what we can show is that, again, going back to the definition of the greatest common divisor, right? So what is it? The greatest common divisor is the largest of or, the common divisors, okay, right? And so any common divisor, in this case, any common divisor of A and B, for instance, always divides the greatest common divisor, right? So that property can be proved, right? Can be proved using this Bezout's lemma, along with the actually the third property of the theorem we just talked about. Okay. So I'm out of space, so let me move to next page. So here's the property I want to prove. I don't know. Maybe I can just call it theorem. Okay. Okay. So if C is a common divisor, common divisor of A and B, then A divides, oh sorry, C divides the greatest common divisor of A and B. Okay, so here's proof. Uh, I'm going to use it. Oh, oops. I'm going to use uh, a different color, like I did before. So proof by Bezout's lemma Before we do that, yeah, I think that's all right. Okay, so by Pesu's lemma, okay, Pesu's lemma, we know that there exists always there exists x and y such that the greatest common divisor of AB can be written as AX plus BY. Okay. Now, since C is a common divisor, of A and B, C divides A and C divides B. This implies that, okay, this implies that C divides the linear combination of A and B, this particular linear combination, right? But for any, I mean, in this case, C divides any linear combination of A and B. So of course, it divides this particular linear combination AX plus BY by property 3, right? By property 3 of the theorem we talked about earlier, right? But then this AX plus BY is what? It's same as the greatest common divisor, okay? So we just proved that C divides, the greatest common divisor. So, with this theorem, with this theorem, we can actually come up with an alternative definition of the greatest common divisor of two integers. Okay, so here's an alternative definition of the GCD. So C is so an integer C is the greatest common divisor of two integers a and b if c divides a and c divides b. And second property, so the earlier definition, that we have seen, that's like the most that's the definition we are mostly the familiar with, right? So again, like the name suggests, greatest common divisor. So it is the largest of all the common divisors, right? Okay, but it can be replaced by the following definition. So first, it's got to be a common divisor, and then if D is a common divisor, so if D divides A and D divides B, which means that D is a common divisor of A and B. D divides both A and B, then D must divide C. Okay, so you can immediately see that the two definitions are the equivalent. Okay, two definitions are equivalent. In fact, we can quickly check that. Say, assume that assume the previous like definition. Okay, so the earlier that's our definition of greatest common divisor. So it is the largest of all common divisors. But then you can actually deduce this definition. So the first part is same, right? So all you have to do is to check second definition, which actually we just proved it, right? We proved it by the preceding theorem. Okay, so we got there. Now this time, so this alternative definition is our definition of the GCD, and we can deduce the earlier definition. All right. So again, first part is same. So second part, so this is what we have as definition. Okay. So if D is a common divisor of A and B, then D divides C. Okay. So in this case, we call C the greatest common divisor, the GCD. Since the D divides, right? Since D divides C, so clearly D is less than or equal to C, which means that C is the largest of all common divisors. So we can deduce the earlier definition, right? Okay, the first definition we came up with. So now you can see that those two are equivalent definitions. Okay, so that's it. More details of my discussion here in this lecture can be found in my lecture note at the following address. And this address is I hyperlinked it, so all you have to do is just click on it to get there. And also, as usual, if you are interested in visiting my main blogger site, just click on this word blogger, which is also hyperlinked. Okay, so it'll take you there where you can find my many other lecture notes in different subjects of mathematics and physics. Okay, folks, thank you very much for listening and watching my lecture. Bye-bye.